Minimize. So yeah, we've taken a little bit of a break, and now we want to get back to the chemistry part of it. And oh, I don't know why that's black there on the bottom. That's okay. It's a little computer glitch. We'll be fine. And so what we want to talk about today are elements of the periodic table. So we started talking about classification of matter, right? We talked about pure substances and mixtures and homogeneous and heterogeneous. And then we kind of came back to the other side and talked about elements and compounds. Then we talked about the physical versus chemical properties of these things. And now we're kind of going back to that classification of matter. And we're now going to focus on that left-hand side of the classification of matter, where for the next couple of lessons we'll be talking about the elements themselves. All right? And then we'll talk about today the periodic table and the way the elements are kind of distributed on the periodic table. In the next couple of days, we'll be going over theories of atoms, right? The atoms themselves and the way the particles are distributed in the atoms. And then we'll talk about how those atoms can form ions, all right? How they can gain and lose electrons. So for the next 2 or 3 days, we're going to be focusing on atoms themselves and the way they behave. And that's kind of on the element side of it, just the elements. Once we're done talking about the elements and the atoms and the way they behave, we can put two elements together and have them react in some way to form a compound. And then we'll deal with the compounds, obviously. And we'll do that for a few days. And then once we get the compounds figured out, which is quite a bit because we have to learn how to name the compounds, but once we're done the compounds, we can then get into talking about chemical reactions. What happens when we put two chemicals together, two compounds together, how do they react? So that's the logic behind the order in which we do things. We're starting with the simplest things, the elements and the atoms and the way they behave. Then we'll put them together to form compounds, and then we'll put elements and compounds together to form chemical reactions. Okay, elements in the periodic table. I think during my babbling, you have all had a chance to write that title down. I'm just going to have a series of kind of rules that go along with the periodic table. And I have a periodic table obviously up here at the front of the board. The periodic table that you're going to use is on the reference sheet or the resource page. I think I called it a resource page on your site. I should call it a reference page. It's really where to find the reference tables. And your periodic table that you're going to use in tests and quizzes looks like this. If you haven't had a chance to look at it, all right, and it has lots of information on it, and I'm going to be pointing out to you where to find the information. But essentially, all periodic tables have 3 or 4 very important pieces of information in each of those boxes that represents the periodic tables. I have all kinds of periodic tables. The periodic table that I've developed for the seniors looks a lot like your periodic table, but even if you can't see the information, you can see that it's a lot fuller of information, and that's because we use more information. But I based it on the same table. I just deleted the data away that you didn't need. So this is on your resource page, and this is the one that I'm going to be giving you when you do a quiz or a test. But you might have gone online and maybe just did a Google search to look at some periodic tables. I don't think you needed one yet, but you're going to need one for today's homework. And you can find all kinds of periodic tables. I get periodic tables given to me by various colleges. Here I got like a whole stack of them that came from, this looks like St. Clair College out of Windsor. And again, you can see the general shape, but you'll always have a certain number of bits of information that are always there. And the first one is the atomic number. And that atomic number is usually the big number, very often in red if your periodic table is colored. In this case, this is also in the upper, when you're staring at it, this one's in the upper left-hand corner, this is in the upper right-hand corner, but this is the number of the order of the elements. And it's very simple, starting with hydrogen atomic number 1, helium atomic number 2, lithium atomic number 3, 4, 5, 6, 7, 8, 9, 10, etc., etc., etc. All right? Now, the atomic number is very important. it distinguishes what element it is, all right? Now, I don't know, did you talk about the periodic table last year in grade 9? Did you talk about what the atomic number represents? If it's a neutral atom, it's the number of electrons. Yep. The number of protons. Does that sound familiar to everyone? Excellent. So it indicates the number of protons. You already know that. That's good stuff. That means on our periodic table, there are 3 pieces of information that actually tell us the same thing. If I told you, what element was atomic number 6, or I asked you, what element has 6 protons, or I asked you, could you please locate the element, what element am I talking about? 6 atomic number, 6 is the protons, you're all kind of scanning for it now. Yeah, Marissa? Carbon. If I said, could you please find the element with the symbol C? All of those pieces of information are actually the same information, and that identifies our element. And it actually determines the chemical properties of that element. It makes it carbon, okay? So those 3 things tell us the same thing. So the atomic number distinguishes one element from another, and you know what? Let's add that, right? Since you guys already know, I'm going to add this underneath, right? The atomic number is the number of, I'm going to put up there a little P plus. That's a really terrible P plus if you're watching this video. That is supposed to be a lowercase p with a plus. What do you think that lowercase p with a plus stands for? Yeah, proton, all right? So the atomic number is the number of protons in the, we're jumping ahead, but where are the protons found? Yes, sir? The nucleus, in the nucleus. So since you've already got that information from the past, we'll just add it in right there. Does that sound familiar? All right. Let's learn more about our periodic table. Now, in a moment, you're going to draw a sketch of the periodic table. Actually, if you downloaded or printed on today's lesson date, you would have downloaded a blank periodic table. It's going to make your life a little easier instead of having to sketch it. If you didn't print that off, right, then you might have to sketch your own periodic table. So you don't have to draw this in, because in a moment you're going to do that. But our metals are located on the lower left-hand side of the periodic table. Our non-metals are located in the upper right-hand side of the periodic table. And there's a very important stair-step line that runs along there that divides the metals from the non-metals. All right? And that stair-step line runs along boron. And then once you come down the side of boron and you cut across, as you work that way across, you will have the stair-step line. So in this case, our stair-step line runs along here like this. All right? And you'll notice here that the ones flanking the stair-step line, they're called what we call the metalloids, and they have properties of both. Now, actually, let's write down underneath this note, not on the table, define metals, all right? Write that definition. Non-metals, write that definition, and metalloids. And in a moment, you'll get a chance to label that on a periodic table, okay? Just write the definitions down. So all metals are shiny, malleable conductors. They're all solids except mercury, which is Hg. We'll learn the symbols a little later on in today's class. What does it mean to be malleable? I don't know if I've had this discussion with you guys yet. I don't think so. What does it mean to be malleable? Yep. It can be, sorry, what did you say first? You're close. I don't know. Did you say can it be thinned out? Is that what you said? The folding part is kind of part of it, but it's the thinning out, that you can hammer it and spread it out, that you can hammer it into a thin sheet. And I guess if you can fold it, that's true as well. Spreading into the long wire is a different word, but metals are also this property as well. What is the term to pull it into a wire? Anybody know? It starts with the letter D if you've heard of it. Yep. Yeah, ductility, or to be ductile. So ductile means you can pull it into a thin wire. Malleable means you can hammer it into a thin sheet. And that's true. Yeah, so that's good. That means we can kind of mold metals. They're kind of soft, actually. Dull, brittle means if you were to strike it, it were to break as opposed to kind of spread out nicely. They're solids, liquids, or gases. Metalloids have the properties of metals and non-metals kind of together. They're right flanking that line. You'll notice that on the stair-step line, the metalloids here, what element is in this space? Just check your table there. What element's in that space? Yeah, notice they don't have aluminum as being a metalloid. And also down here, what's this guy? I really don't know that guy. What is it? The polonium? Is that what we're looking at? Polonium? Polonium? P-O? Highly radioactive. You wouldn't be dealing with a lot of polonium, hopefully. If you were to ingest some polonium, it would kill you quite quickly. So we don't want to work with it. Anyway, it's flanking the stair step, but these elements, look at that, looks like an A, it's supposed to be an O. These elements exhibit a little more metallic properties than the other metalloids. So they've kind of designated them as being metals. Like aluminum is a metal. We, put pop in aluminum cans and all that type of stuff. So they don't count that as a metalloid. All right, that's kind of tricky because it is along the stair step, but it's not part of that group. Hydrogen is an exception, even though hydrogen is in this position on the left-hand side, right? It's a gas and does not contain those properties. All right, so it's a special case. Okay. Number 3. The structure, and we're talking the structure of the table, right? We're obviously talking about the periodic table. The structure predicts physical and chemical properties. So the location on the table can tell us the way it behaves. The letter colors tell us the state, and maybe it wasn't such a good idea to put solid is in black because you can hardly see it. That's what that says. So this says solids on the table are the black elements. Liquids are the blue elements, and gases are the red elements. On this table that I'm going to give you when you write a test, because I printed it on a regular black and white laser printer, you can't see the colors. They're actually different shadings. If you go home and open the reference table and download the periodic table and print it on a color printer, you will see the colors. All right, it'll indicate those. That's a universal thing. Again, on this particular table, which is yellow and black, you can't see the colors, so you can't really get that idea. But on this table, in this case, the gray represents the black. Those are solids. The blue is obviously the blue. And then the red is obviously the red. Those are the gases. Yep. The white are artificially made elements. And if you want to know how they artificially make elements, you want to look up things like particle accelerators. The Large Hadron Collider is a very special particle accelerator. We'll talk about that more in grade 11 chemistry. But they fire protons and neutrons at certain atoms, and they can get them to stick, and they can actually change the elements into different identities, all right? And they tend to be very short-lived. They're highly radioactive, so the moment that they're formed, they tend to blow apart and disintegrate into other elements, okay? So they exist for such a small period of time that they haven't had them in existence long enough to test what their physical state would be. Does that make sense? So in a particle accelerator, they'll hammer an element maybe like uranium. Actually, you know what? Plutonium, they know it's a solid. So this does exist for a long period of time. So in this case, this simply means artificially made. Artificially made elements. All right? It means that they've been made in nuclear reactors and various other things. Because I do know that they do have plutonium and it's solid. Plutonium is a solid. To be honest, they're all going to be solids because they're way down here at the bottom. They're all metals. They all have that solid characteristic. So it means artificially made. Some of these way at the end don't exist very long. They've come into existence and poof, they're gone. All right? As you move from the center of the table towards the bottom and left and the top right, the reactivity of the elements increases. So in the middle, we've got some very non-reactive things. Silver, gold. Gold is very non-reactive. Silver is slightly more reactive. If you have silver jewelry, it can tarnish. It can like get a kind of a gray coating on it, and that needs to be cleaned off. But gold doesn't tarnish. It does not react with oxygen. As you move to the corners of the table, and the corners are not down here, but the corner is down here and up here. As you move to the corners, the chemical reactivity increases. They become more reactive, except for this group. It's a special group. We'll talk about it in a moment. What is group 18 called? What's group 18 called? Anybody remember? Oh, that's group 17. Move over one. Yes, sir? Noble gases, because they don't react very much. So this is a special group. We'll be talking about the groups in a moment. All right? So our highly reactive ones are up here. Fluorine, very reactive gas. Francium, very reactive metal. All right? Cesium, super reactive. All right, let's roll on. So now let's talk about, and I'll bring the whole thing up here. I hate animations. I hate them. I hate them. All right. So now let's talk about some of those chemical families that you've learned in the past. And have you talked about these before? Grade 9? Excellent. Good. So this is a review. Awesome. So we call them families or groups, and they are the vertical columns. And if we have issues with vertical, we're talking about these that go up and down. Because the horizontal ones are like the horizon. I want to add something to alkali metals. I want to add very reactive. They're far from the center of the table. They are very reactive metals. They react with the air. They react with water very violently, producing light and heat. Sorry? Well, it was very difficult to discover them. Many of these elements, they were discovered, and I got to think about what time we're talking. Late 1800s. No, not late 1800s. Mid 1800s. But it took them a long time to discover these because you cannot dig a hole and mine for sodium, because it doesn't exist as a hunk of sodium. Because it's so reactive, even in nature, any drop of water it encounters, it reacts and turns into a sodium ion. It turns into salt, right? So you can't find it as sodium. Like silver and gold, you dig a hole in the right spot and you can find some gold. Way to go, right? You may walk down the street and say, oh, look, there's something shiny. Pick it up. Oh, look at it, somebody's ring. It's pretty. Am I going to turn it in? Or am I going to put it in my pocket? Anyway, that's a different story. But anyway, you can walk down the street, you can find a piece of gold or gold jewelry, but you will not walk down the street and say, whoa, look there's a hunk of potassium sitting right there. It's not going to happen because it is so reactive, it would have reacted. They had to do a process called electrolysis in order to separate the ions and turn it into metals. Did your teacher last year show you something called the Huffman apparatus that separated hydrogen and oxygen? If you were to use a similar apparatus, but it's very difficult. If you were to use a similar apparatus except with a solution, but you can't use a solution, say on potassium chloride, and you separated the potassium from the chloride, you can't do it in a solution because as soon as you make the potassium, it's in water and poof, it disappears. So you have to actually melt the solid. So you'd have to take salt, like salt crystals, sodium chloride, and melt it, like super hot, melt the salt. Then you put electrodes in it, and you do the same experiment, and because there's no water there, you would separate it out and you'd get the metal. You'd get that metal out. That's how it was discovered. A difficult thing to do, we can't do it in the laboratory because our Bunsen burners don't get hot enough to melt salt. So difficult thing to do and dangerous. You don't want molten salt in a laboratory in a high school. Oh, molten salt, whoops, spilled it on me. That would put a hole in you, I would think. Wouldn't be good. Alkaline earth metals, all right? So still a little reactive. They don't dissolve very well, the compounds. Halogens, so groups 13, 14, 15, 16, just not exciting. They're important, like it contains oxygen in there, that's really important. But they're not so distinct that they have their own name. Group 17, the halogens, again, highly reactive. You might already know what makes this group 1 so reactive and what makes this group 17 so reactive. You might remember from last year, thinking ahead, or thinking back. I guess you're thinking back. What made them so reactive? Yeah, Wilson? It has everything to do with their outer orbits and how they get electrons. Yep.
Isn't it that the noble gases have like a full orbit already?
Yep.
The group 1, the alkali metals have like they have
they didn't have a lot. How many did they have? Anybody remember? Yep. They got 1. So if it gets rid of it in some kind of chemical reaction, then it's going to have the same outer orbit as the previous noble gas. Excellent. That's why. And what about these guys? Yep. They're going to gain 1. How many do these guys have? Do you remember how many outer electrons this group 17 has? Sam's got an idea. Just moved, then he did the scratch move. 7. It is 7, correct. Yep. And what's the desired outer shell? Yep, Marissa? 8. Does that sound familiar to everybody? We'll be going over that again in detail in the next couple of days, but that's the exact reasoning. Noble gas, they got the full outer shell. Transition metals, they're here in the middle. They don't have special names. Their properties are very similar when you get into the middle here. The way their electrons exist in their shells are very complicated. All right? In actual fact, I'm gonna blow your guys' minds here for a minute because I usually teach the grade 11s and 12s. We now know that they don't exist in nice little shells, right? That picture on the wall back there above Yoda, you see all those funny shaped things? Some of them look like donuts, and others look like they almost look like Mickey Mouse's ears on the right-hand side, and in the middle they almost look like 4-leaf clovers and all kinds of funny shapes. That's where electrons exist. We now know that they don't exist in these nice little shells. And why am I telling you? I'm not trying to confuse you, but when you get to grade 12, I'm going to be teaching you about those shapes, all right, and how it works. But what I wanted to say was, in the middle here, where their electrons reside, are really quite complicated. but it makes their chemical properties very similar. So their electrons really hang out in very similar spots. That's why when you drew Bohr diagrams last year, and we're going to do it again, you didn't bother drawing them of the guys in the middle here because their electron configuration, where their electrons are configured, is quite complicated. And that's the transition metals. Okay? All right? Just ignore those funny shapes. We're going to go with nice rings for another year, 2 years. And then I'll mess with your minds in grade 12. Lanthanides. The lanthanides are these guys down here from 57 up to 70. Okay? And we're not going to talk about their properties either because they're very similar. And those funny shapes at the very bottom there, oh, very complicated. Even in university, I did not learn and worry about the chemistry of these guys down here because it's complicated. We'll just say it's complicated. But it is important to understand where they exist on the table. Okay? So if we're running through the atomic numbers, we run along there 2, and then 10, and then 18. We go to the front 19 to 36. We go to the front 37 to 54. Okay? We go to the front 55, 56. This chunk in here is actually meant to exist in this space. And all of these transition metals really should shift down 14 spaces in order to make that fit. But it wouldn't fit on a nice piece of paper if we built it that way. So what we do is we simply say, okay, take a detour, 57 to 71, and then 72 across to here gets us to 86. So that's the lanthanides because the first one in the group is called lanthanum. So it's just what follows lanthanum. All right? Then when you get to the front, you're at 87, 88, and you take another detour here to 89, down there to 103, which then brings you back up to 104. And again, the first guy in the row is actinium, and therefore they're just simply called the actinides. All right? Their chemistry is very similar again, so their chemistry is not interesting to us. Their nuclear characteristics are awesome. We've got uranium, which runs our nuclear power plants. We've got plutonium, which can be used in power plants and bombs and things like that. So their nuclear properties are pretty exciting, but their chemical properties, we're not that worried about them. Okay, let's define what a period is. So a group is up and down. A period is the horizontal row. There's 7 of them. And remember, horizontal, that's our left and right. For those who maybe don't know, I'm going to go on the assumption there's maybe some of you out there. Horizontal, which way is that again? The horizon, that's what I said. That's how you remember it. The horizon. That's the way to do it. Now that works fine here in flat Lambton County. I suppose like if you lived in like Italy or France in the Alps, the horizon could do all kinds of weird things, couldn't it? Are my jokes just not funny? Or is it that you guys are just so serious into learning? I'm going to go with the fact that you're so serious.
No, they're not funny.
Thank you. Thank you. They are funny, Allison. You go straight home and tell your dad how I crack you up. So, period numbers. This particular periodic table numbers them. 1, 2, 3, 4, 5, 6. Technically, the lanthanide series is in period 6. All right? And then 7. And technically, the anthanide series is in period 7. All right? The table that I give you, I'll be darned, I do have the periods numbered on them. So they're numbered on that. So when you have a test to do, you're going to have the period number numbered. Right? Sometimes they don't have it. Oh, this one has it numbered too. Sometimes they don't have it. You got to count. Right? It's kind of a pain. You got to count down, but these have them on it. Okay? All right. They indicate the number of orbital shells that exist in the atomic structure. So when we start drawing the Bohr diagrams, there's going to be 1 ring, 2 rings, 3 rings, 4 rings, etc., etc. Okay? Even though those funny shapes are what really exists, but we're not going to worry about that right now. You guys can go with rings. All right, so now at this point, if you have your blank periodic table there, whoops, I want you to label it now. So if you've printed that blank periodic table, excellent. If you haven't printed the blank periodic table, it's not very hard to sketch one. So I'll sketch one with you. You can then label this. To sketch a periodic table is not very difficult. To sketch a periodic table, start with that left side. All right? Yeah, because I want you to be able to label that at some point in time. So start with the left-hand side, and it takes a couple of little steps. 1, 2, with the second one a little longer. Now notice, I really don't care about the individual boxes. I only care about the groups. So I don't need to draw all the periods in my sketch. Move across a little bit. I really don't care how much, because we're not actually going to make all the individual boxes. Move back up to the same height as this, then move across like this, and then move up 1 and down. All right? Then I would just close it off like that. Because then you can do something like this. And then you're able to label the important groups. If you want to number them, you can go 1, 2, 3, 4, 5, 6, 7, 8, 17, 18. You know that there's numbers in the middle there. I don't care what those are. Right? Does that make sense? So all that other stuff in the middle, not a big deal. You can then label your alkali, your alkaline earth, your transition. This doesn't have a name, your halogens, your noble gases. Underneath, make a little rectangle, cut it in half, label your actinides and your lanthanides. All right, so that's not too tough. And you know what we could add on it? And I'll put it up here first for those who have the blank one. Let's add, and let's make this a little darker. Let's add this. Right? And somehow indicate that the metalloids are kind of flanking it. Right? I don't know how you would do that. You could maybe put an arrow to that side and an arrow to that side, and then say metalloids. You know, does that make sense? Does that kind of cover what we're talking about? It includes those guys that are on both sides of it. How would you do it on this one? Again, I wouldn't get too worried about it. I would maybe go something like this. We get the idea. Do I have a metalloid that's in the halogens? I guess technically I do. But again, I wouldn't get too stressed about it, and I would indicate the metalloids are close to that stair-step line. We have many perfectionists in this room, I can tell. My picture's a little too loosey-goosey for some of you guys. Oh my goodness, he's just drawing a sketch. I need my ruler. So I'm getting a sense this is quite a bit review. Excellent. Now, next slide has a little example on how to identify. I don't think it's worth our while writing it down. Let's just go through it kind of together orally. There is a worksheet that is also on today's date that says, you know, identifying this element. Is it a solid? Is it a, you know, all that type of very straightforward stuff. So you'll have a chance to practice that on the sheet. There's also a little bit of work. But after that slide, I do want to talk about the chemical symbols and the rules associated with the symbols of the elements. And then you're going to be responsible to learn the names and the symbols of the first 20 elements, plus about 10 other very important ones. And then we're going to have a quiz in the near future on being able to name, get the name from the symbol or getting the symbol from the name. So we're going to finish off today's lesson with talking about the symbols and the way they behave, or how we treat them. How are our sketchers doing? Not good. Stress, where did it come from? Who said not good? So too much stress over this loosey-goosey sketch?
No, I'm trying to like.
All right.
It's taking longer than.
Okay. Well, I may advance before you're finished, but it's always online. You can go back and check it. Go back and finish it off. All right, I'm doing it. I'm moving. I'm doing it. Can I move, Wilson? Can I go? See, he's probably an awesome sketcher. His sketch is like, done. Nice job. No. Nice. Very nice. You've got flip-flops on today. Do you own Skechers? No. Oh, okay. Okay, let's quickly go through this. So, let's locate gold on the periodic table. If you've got one that you've printed out, awesome. If not, you're staring at my my large periodic table here. And what period is gold in and what group is gold in? Allison, what do you got? Period number is 6.
And
11 is the group. Awesome. Lead. The group is the top one that you look up and down with. The period is this guy. All right? So what do we got for lead? Yep. 6 and 14, is it? I'm going to just do a quick check. 14? Where is it? Oh, yeah, 14. Nice. And what element is located at 6 and 1? 6 and 1. Yeah, go ahead. What's the symbol?
Yeah.
Yeah, cesium, CS.
Okay.
Cesium, CS. Wouldn't hurt for you guys to print out that table, but that's okay. And what about 3 and 17? 3 and 17. Yep. Chlorine, right there. 3 and 17. All right? You don't count down from the top. It's got to be the row. Excellent. Chlorine. Cl. Any questions or concerns on locating our elements? Very straightforward stuff. All right. Symbols. I do want you to write down, I want you to write down this whole slide. The entire slide on this one. Oh, yeah, I figured that would be the case. You don't need the squares for your sketch. Yeah, that would do. Okay, all right. Well, that would take you a while. Yes?
Don't some of the elements have 3 letters?
They do. They're getting away from them, though. I'm going to explain where they come from, and I'm going to just leave it with the 2 letters, because they're actually going back to just 2 letters, all right? And I'll let you write a little bit more before I tell the story, because many of you probably don't like it. Yes, Wilson?
Where is they? We decide.
That's what I'm going to talk about in a moment. All right, so you get that written down, then I'll tell the story, because I know you like to listen rather than write. So you write, and then I'll tell. Now, I must admit, I can tell you who decides right now, but I can't remember the name of the scientist who originally decided to go with the two-letter element symbol. So I'm going to do as your generation does. I'm not going to actually think about it too hard. I'm just going to Google search it. I'm not going to find it because if you put in element symbols, you get all kinds of, you get the symbols. I want to know the scientist who came up with the symbol method. I got to track that one down. Current symbols, symbols not used, symbols, other symbols, references. Yeah, I've got here, I've got element symbol origin. I could add scientist to it. Chemical elements, history of the symbols. Oh, that's a hot one. That's a good one. What? It wasn't him. The symbols. Okay, Dalton. Oh, that's awesome. Ah, there's his name. His name was, last name Berzelius, Berzelius. 1813, 1814. Now, unfortunately, I can't transfer this screen over to this one. Just to give you a little rundown. This guy, Antoine Lavoisier. Have I talked about Antoine Lavoisier yet in this group? No? Antoine Lavoisier is considered the father of chemistry, all right? Antoine Lavoisier lived in the early 1700s. He was a French scientist. He was also a tax collector in Paris just before the revolution and ended up getting his head cut off with the guillotine because I don't know the history of it, but what happened? The peasants took over or something like that. I have no idea. Anyway, so he ended up, guillotined at about like 35. He died quite young. Anyway, he is essentially the equivalent of Sir Isaac Newton to physics, right? So Newton is like really kind of got physics going properly, and this guy kind of got chemistry going. And he did have a list of elements, right? He created a list of all of the known elements at the time, and he actually named many of the elements, but he didn't have any symbols for them, all right? The next guy to come along, very important, is a guy by the name of John Dalton, all right? And John Dalton was in the early 1800s, so about 100 years later, and he really kind of came up with the first atomic theory. We're going to talk more about him when we talk about atoms in another day or two. But Dalton used a series of symbols like circles, like a circle with a star in it was one particular element, or a circle with a cross in it was different, a circle with a little shape in it. So he had actually pictures for the elements. But according to this Berzelius guy, around 1813, 1814, he decided to use the Latin names or the names of the elements, and he used the first two letters, with the first one being a capital, to represent the symbols. So this is 1813, 1814, where these letter symbols are coming into play. All right, so that's where these come from. Now I said to Allison there. Allison asked, "Don't some of them have three?" And they do. That's because a handful of years ago, the group that's now in charge of naming, decided instead of naming elements like after people, why don't we just name the elements, not right now, Mark, I'm busy, okay? Why don't we name the elements based on their number, all right? So this group of they is part of a group that's called the IUPAC, and it stands for International Union of Pure and Applied Chemists. And it's made up of a bunch of really old chemists that get together probably once a year in Switzerland and probably party it up pretty good, and then they have meetings and they decide what they're going to call things and what the rules are going to be. So they decide the rules of chemistry, very senior chemists in the world, okay? And they decided, instead of calling them after people, why don't we just name it after the number? So let's use a little bit of Greek. So 110 would be nilium. Nil, 110. Unium. Get the idea? Bium. 2 by. And so that went on for probably about 10 or 15 years. And then they must have sat down and said, this is really dumb. Let's go back to honoring our scientists, with an element if they discovered it, or even if they didn't, let's let the people who discovered it help put input on who they want it to name after. So they got rid of a lot of these. I have periodic tables that have nil quatrium, nil pentium, and so in the past 5 or 6 years, they've given 104 to Ernest Rutherford, Bohr-Rutherford diagrams, Rutherfordium. This guy you don't know. Seaborg, he's pretty important in creating artificial elements. Look at 107 is borium. The Bohr diagrams, right? So we named it after borium. Who have we got here? Actually, they finally gave one to Mendeleev, who actually invented the periodic table, Mendeleevium. It's a mouthful, but MD Mendeleevium is in honor of Mendeleev, who actually invented the periodic table. Yes, Wilson?
Okay, I have a couple questions.
Yep.
Okay, first of all, so before, if you discovered an element and didn't get to name it, they named it after the number?
In probably the 1930s and 40s, then actually, the IUPAC originated in the 1930s and 40s. And so they kind of, as a group of senior chemists, took over the naming. Yes, so if you discovered an element, at that point, you kind of lost your ability, because this group said, we're much smarter than you guys, so we're going to control the names.
All the ones on the bottom, like Nobelius.
Nobel did not discover that. That was given in honor of him.
I thought somebody...
Now right here, polonium, all right? This was discovered, it was a radioactive element discovered by Marie Curie. Have you heard of Marie Curie before? Very important female chemist of the late 1800s. She discovered this element and she named it after the country she was born in, Poland. She called that polonium. But once the IUPAC came along and they made this governing group of chemistry to kind of govern the rules, you lost that ability. Yep. So some of them are, and some of them aren't. I got to keep going. I'm looking at the time. Now, very important. First letter must be capitalized. Second letter must be lowercase when you do the quiz, right? Some people just put all lowercase. I'll be taking marks away for that. Everybody understands that? Some of them are named after the Latin. Many of them are now being named after, in honor of scientists. 99, the Wayne Gretzky of scientists, Einsteinium. That's how I remember it. Einstein was pretty good at what he did. Wayne Gretzky was good at hockey. Anyway, Einstein never discovered any elements. He was not a chemist. He was a physicist. But he did have many theories that helped develop the atomic theory. So now, you don't have the ability. You can write this top bullet. You will need to learn the names and symbols for the first 20 elements. Now, I'm not going to give you time to copy that down because time is ticking away here on the class. You can find your periodic table and you can make that list yourself. If maybe you don't even want to make the list, maybe you just want to study it right from the periodic table, then you don't even need to write that down. But that's up to you. But like I said, in a few days, not tomorrow, but obviously into next week, I think it might be Tuesday or something like that. Wait a minute. Is it Monday? It's already on my thing as Monday? Excellent. Good checking my calculator, or my calculator, my calendar. Oh, excellent. Element name quiz. We're doing it on Monday, right? So, you need to know the names and symbols of those. First 20. Yep. No, I'm not concerned about that. Some teachers make you do that. I don't, and I'll explain why in a moment. And these, and those you do have to write down, because they're significant. We use them a lot. The logic behind making you know what order they are, really, why do we make you do this? I've even had a debate with some teachers saying, do you make them memorize the elements? I don't do that anymore. They get the periodic table. And I say, yeah, I make them memorize the elements. By using the table to memorize your elements, it also guides your eyes to use and locate things on the table. When you get into grade 11 chemistry, and even right now in this class, I ask you about so many elements. In one question, you might have to look up 7 or 8 elements. Just one little question that should take you about 5 minutes. If you can't find the elements on the table and you've got to go from one all the way to the end trying to find the element, you'll never get the question done because you'll be slow. By getting you to use that table to memorize the elements, if I ask you to find nitrogen, I'm hoping you can bring your eyes to nitrogen and do your thing. Get the numbers that we need. Find the atomic number. Find the mass number. That's why some teachers also make you learn the order, right? So that you memorize the order they come in. But I think if you just memorize the names, you're okay. To get the number itself, you can get that on the table. The number can be found. So many of these elements are very important. They're important just in industrial uses, iron, nickel, copper, zinc. Some of them are biologically important. Iodine's important. And those. Yeah, first 20 and those. And the quiz will just simply be 10 names, give me the symbols, 10 symbols, give me the names. I'll just pick randomly kind of 10 and 10. All right? Yes, there'll be 2 lists of 10. One, you'll give me the symbols. The other list, you'll give me the names from the symbols. Just go back and forth. I don't know if you guys have figured out yet, but on the bottom of my little thing there, it tells me how many slides I have and how many we need to go through. And you can see on that 12 of 12, so that's the end of today's lesson. There is a sheet online, all right, and I'm going to show it to you right now. So the sheet online, you'll notice here's the 11th. There's the handout. There was the blank periodic table that you could have printed. So the handout essentially has questions very similar to what we did in that quick little thing together, right? Period number, group number, what state is it in, metal, non-metal, metalloid. Same thing, what group do you find this in? And then there's some textbook questions that you can then do on a piece of paper or whatever. Everybody catch that? Now, these sheets that I'm not collecting in, I'm starting to get them done myself, and I then use my phone to scan the picture in. So if you go back to course content, and you go to chemistry, the homework solutions are starting to get in there. They're starting to fill up. Because we're going to have lots of little worksheets in the next couple of days. Here we've got the structure of the atom. This is the exact sheet. You can see I've also got some handwriting on there. Those are the answers to that sheet. You can check your own sheet. All right? The next sheet we're going to do, Bohr diagrams. We're doing Bohr and Lewis diagrams tomorrow. There's the answers to that sheet. The day after, we're doing formation of ions. There's the answers to that sheet, all right? This is naming of chemicals. When I assign that sheet, there are the answers to those. And as we get moving ahead, I will be completing the answers, and I'll scan them and put them online, and you can always go and get them from the course content homework solutions. Okay, so you can check that tonight when you're done. You can even have it on another page. You can work away and you can flip back and forth. Make sure you're doing it right. Okay? All right? Okay. Where's my recorder?